Okay, we can begin. So today's second talk is by Minxi He from IBS South Korea, and he's going to talk about unitarity of Higgs inflation and UV extension.
Okay. Thank you very much. First I would like to thank the organizers to give me this opportunity, and I'm very happy to give a seminar here about my work. And this work actually most mainly based on these four papers and with collaborating with these people. And as suggested by the title, today my uh, talk will be about the Higgs inflation. And Higgs inflation suffers from the unitarity problem, and then I will discuss how we can save this model by the UV extension. So just make sure everyone is on the same page. So I will give a brief introductory part about inflationary cosmology. From the Hubble's law, we know that the universe is expanding, and also we have already discovered the cosmic microwave background, which is the CMB. Yeah, CMB. And then we found that actually our observable universe is so homogeneous and isotropic and flat, which actually cannot be naturally explained by the very successful theory, the Hopper band theory. So unless we determine the initial conditions for the heartbeat band very precisely. Otherwise, this we usually consider it as the initial condition problems for the heartbeat band. So in the 1980s, inflation was proposed to as a solution to these initial condition problems to explain why the universe is so homogeneous, isotropic, and flat on the large scale. Okay. And so-called inflation actually is a period when the universe experienced accelerated expansion in the very early universe. Okay. And because of this accelerated expansion, all the inhomogeneity and isotropy or something and spatial curvatures will be kind of diluted, such that it provide proper initial conditions for the hot Big Bang. So in this scenario, there are two major problem or questions we need to ask. The first one is what drives this inflation? Yeah. And the second one is after inflation, how to connect the to the subsequent hot Big Bang and the evolution of the late universe. Okay. And we know that in GR, with only the Einstein-Hilbert term, we cannot have such a kind of accelerated expansion um, in the early universe. So we need to introduce something else. And of course, we can introduce a cosmological constant, which can give us the zeta space. But the zeta space has another problem, is that we cannot have a graceful exit to connect with the Hubble band. So basically, we need some dynamical matter field, which we call the inflaton. And usually we consider it as a scalar field, okay? Or one or more scalar fields. And then these matter fields will enter the Einstein equation and then tells the universe at which time and we need to expand. And then inflation happened. And after inflation, the inflaton, uh, presumably, it coupled with other matter, standard model particles or something like that, and then it would decay. Then with the process we call reheating, and to produce this entropy and other standard model particles, such that we can smoothly connect to this hot Big Bang evolution of the universe. And so when we try to find such a appropriate matter field to serve as an inflaton, uh, it's very natural that we look back into what we have already known pretty well, which is the standard model of particle physics. And inside this standard model, we have the only one discovered scalar field, which is the Higgs field. Okay. And in this scenario, we call in this kind of model, we call it the Higgs inflation model, which means that the Higgs plays a role as the inflaton. Okay, and the standard model Higgs, we know that it is a complex doublet. So actually, it has like 5 1, 5 2, 5 3, 5 4, four real scalar part. And uh, the Lagrangian of the Higgs inflation model is the original one. It's given like this. Okay, you have the Higgs part, kinetic term, and potential. And here I only consider the 5 4 potential because compared with the inflation scale, the electroweak scale is too small, so I neglect the mass term. And the important one important part is the non-minimal coupling, so-called uh, Xi, between this Higgs field and the Ricci scalar. Okay, here the phi square actually is the sum of the phi 1 square plus phi 2 square plus blah blah blah. Okay, and in order to match with the observation, the observed power spectrum of the curvature perturbation, we require the model parameter c over square root lambda to be of order 10 to 4th. Okay, and this is yeah, and but by requiring this, then we can basically match with the observation, and the prediction on the scalar spectral index and the tensor to scalar ratio is favored by the Planck data, okay, which is given here, and this contour is the favored, observationally favored region, okay, and this is yeah, the Higgs field. However, uh, people also ask questions because this is a very well motivated model, and I think it's very promising. And then people started to ask whether this model actually valid as an effective field theory, so-called EFT, because here we have a very large nominal coupling if we consider the lambda, for example, to be 10 to minus 2, 10 to minus 3, something like that. Then this Xi actually is order 1,000. So have a such a high, large coefficient or nominal coupling, then whether the validity of the EFT will break down at some point. So to answer this question, we have to consider the UV cutoff in this model, and also the energy scale of the any process that involved in this whole evolution. And actually, more than 10 years ago, there are many papers discussing this issue, and then they found that actually this, as I will show in more detail later, this large nominal coupling actually will turns out to be a pretty low cutoff UV cutoff scale for the theory. And in this 2017 paper, they show that actually during the preheating process, the um, the particle, the gauge bosons produced during this preheating process will have a momentum larger than this UV cutoff scale, which means that actually the effective field theory breaks down, and we cannot trust any perturbation theory. So yeah. So okay, now we have this research background. Then in the following, I will going to talk about firstly some general thing about this EFT in the early universe. Uh, Specifically, I will focus on this non-linear sigma model, which the Higgs inflation actually belongs to, and discuss how we can extract information from the nonlinear sigma model, no, from the target space of the nonlinear sigma model. And then I will discuss the effect of gravity on this target space, because we know that now we are talking about inflation. Of course, the gravity is very important. So we have to take into account the effect from the gravity. Okay. And after that, I will apply the things I discussed in the first section to the Higgs inflation case, and then show you have to calculate the cutoff scale and how the unitarity is violated in the Higgs inflation. And in the third part, I will talk about this UV extension, especially specifically with the R square term. And yeah, so then we will have this so-called mixed R square inflation, which is a healthy inflation model. And I think it's the most natural extension of the Higgs inflation. And if time still have some time left, I will discuss this so-called Einstein-Cartan Higgs inflation, which recently proposed by Shaposinkoff and his group members, and as a general framework for a large class of Higgs inflation models, including the so-called Platini inflation and the original Higgs inflation. Okay. So let's go to the first part. So the so-called nonlinear sigma model, which actually appears quite commonly in like particle physics or in many scalar tensor theories. Okay, and for example, in the Higgs inflation case, let's forget about gravity at this moment. Okay, we have several uh, n, for example, in standard model n equal 4, we have n scalar fields phi I, and in the kinetic term, we not only have the space-time metric, but also the so-called the target space metric or field space metric. Okay, this tells us how do we sum these different fields together. Okay, and also in this talk, I will focus on this model with the ON symmetry as it is in the example shown here. And also, let's focus on the target space. So let's forget about the potential. Of course, potential can also contribute to the UV cutoff scale. But here, for example, in the Higgs inflation case, we only have the renormalizable 5,4 and small enough coupling, so we don't care about that. Okay. And as you can easily see that we can like take an analogy to the space-time in GR. This field space, actually, we can write it down as this in this form, okay, as a kind of space-time, but the coordinate is the field, okay? And also, when this curly Gij is flat, then which means that the target space actually is trivial, and actually we call it a linear sigma model, okay? But I mean, in general, this can be a function of phi I. So in that case, this it is the general nonlinear sigma model, and we will have non-trivial contribution from this geometry of the target space when we discuss the cutoff or scattering amplitude between different fields. Okay, and here I will show you two very simple examples that we can encounter such kind of structure in the kinetic term. For example, the in a three-dimensional Euclidean flat, space XYZ, and then the metric, of course, is trivial 1, 1, 1. But when we somehow get constrained to unisphere in this space, which is given by this equation, then actually we can eliminate one of the coordinates. For example, we eliminate this z by solving this equation, and then we put it back to the metric. Then we will have such kind of a structure. And this is actually nothing but just a concrete example of this Gij that d phi I, d phi j. The only difference is here we use XYZ, but this is phi 1, phi 2, phi 3. Okay. And the second example is also very similar, and this in the field, in field theories. For example, if we have more than one or more than two fields, phi 1, phi 2, phi 3, something like that, and then it has a potential, like the Mexican have potential, then the field if we put a field somewhere, then inevitably it will roll down to the bottom, this circle of the potential, and with the radius, for example, given by zeta. Okay, so even if you start from a flat field space delta ij, but if the the field configuration is constrained at this vacuum, then actually we have this just the same situation in this case, and then we can, after eliminating, for example, the radial component of this phi I, then we can have a non-trivial target space. It looks like this. Okay, this is exactly the same as this one, actually. So this is two examples that we can, I mean, have a feeling how to, how I mean, what in what situation we will encounter such kind of non-trivial target space. And also by doing the exercise in these two examples, we can immediately see that the geometry of this target space actually is, I mean, naturally connected to the property of the system, okay? Because it reflects how, for example, how the potential looks like or something like that. And so studying the geometry of target space is very helpful for us to understand the system. Also, another very good property of this geometry is that geometry, as we know, it's independent of the coordinate choice, right? So no matter what coordinate system we choose, the geometry is unchanged. So when we try to find out physical quantities or observables, which also should be independent of the description, the way we describe the system, then it is actually analogous to geometry. Like no matter what coordinate we choose, the geometry is unchanged. Okay, so if we can have a geometric method to calculate the physical quantities, then the uniqueness, or yeah, the uniqueness of this kind of quantity is automatically manifest. So this is another good thing about this geometry. Okay, then I will show you, for example, how this geometry is connected to the, for example, scattering amplitude. Um, Given a general, this Gij, for example, we can expand this Gij around some vacuum expectation value, for example, phi equal phi 0. Then we can immediately get some nonlinear terms for some, yeah, Taylor expand. Then you can pick up the like 4-point interactions, and then we can calculate the, for example, this 4-point interaction. And this 4-point interaction is proportional to the center of mass energy square over some scale square. And as we know, unitarity tells us that this should be no larger than unity. So which means that lambda actually gives us the cutoff scale. So yeah, in this case, you can see that this kind of term indeed is related to the cutoff scale. Okay. And actually, this is well established in the EFT community, and they can calculate the amplitude, scattering amplitude, 4-point amplitude, in terms of the Riemann tensor calculated from this target space metric. Okay. This bar means the quantity that evaluated at the vacuum of interest. Okay, so you first calculate the Riemann tensor, and then you evaluate at the vacuum that you're interested in, then you get the answer. And there's a coefficient here, but this can be easily removed, or I mean, put it on the right-hand side by using the field buying technology or something like that. But I will not talk about it here. Anyway, the message I would want to deliver here is that the scattering amplitude is indeed connected with the geometry or the Riemann curvature in of the target space. Okay. For example, go back to this example. Okay. Then we can immediately calculate the scattering amplitude by following this. And we, for example, take a vacuum like pi equals 0, 0, 0, 0. Then we evaluate all, the Riemann tensor at this point, which has a very special structure like this. And this Rik equals 1 over c squared. Then you can immediately get that this pi I to pi j is given by this. This S1, 2 is the Mandelstam variables. Yeah. So it's related to the energy. So you can see that this theta actually gives you the lambda. Okay. Yeah. So this is a very nice geometric method for this nonlinear sigma model. But one thing we noticed that actually we are interested in the UV cutoff, right? The UV cutoff should be kind of, UV cutoff is for the whole system. It's not for only one process. So we need to kind of take into account all the related process. And then we determine the UV cutoff. So, but the Riemann tensor is not enough, which means that the Riemann tensor is not enough because the Riemann tensor has three indices. We can, it is only covariant under the field redefinition, and it will how to say, if we change, for example, the state of this in and out particles, then the Riemann tensor will change, of course, because the amplitude is different. But what we want is something that is for the whole system is not depending on the individual process. So we can use, for example, the Ricci scalar, which actually is kind of summing up all the processes because they summing up all the Riemann tensor. And the cutoff scale then will be inversely proportional to the square root of this Ricci scale. Okay. And then, okay, so then can we use this kind of argument or this kind of technology or method to study the Higgs inflation case? For example, as we can see here, the Higgs inflation case actually has a trivial target space, that ij, which means that if you calculate the curvature, it gives you 0. And which means that there's no cutoff scale from this scalar center, or the cutoff scale is infinitely high. But is this true? No, of course, because we have to take into account the gravity. The gravity will change, for example, this L with we should multiply by square root minus G, and also change the metric here. And another more important thing is that it will change, it will affect the scalar sector through the non-minimal coupling. Of course, in the GR case, this is 1, so we don't need to care about that. But now we have this non-minimal coupling, so we have to take it into account. Okay. And here I just want to define two terminology. One is the so-called Einstein frame, which means that this gravity sector in the Lagrangian just looks like this. Okay. Any other frame that does not look like this, we call it Jordan frame, and it is not unique. You can have many different kind of Jordan frame. Okay. And as a in these two papers that actually, if given some Jordan frame Lagrangian, we can do the Weyl transformation to go back to this Einstein frame such that the gravity sector is simpler, such that we can, have more intuition because we are more familiar with the scalar field instead of this higher, complicated curvature thing. Okay. But once we do this, then actually many things will change. For example, this square root minus G will change, and the Ricci scalar will change. So as you can see here, we have a derivative on this conformal transformation factor. Okay, and if this conformal transformation factor now is taken to be this phi of phi, f of phi, then you will get some kinetic term or derivative, at least for this phi, okay? So then these derivative terms will contribute to the kinetic term of the Higgs field, for example, in the Higgs inflation model case. Then now the geometry of, or the metric of the target space is changed from a trivial flat target space into such complicated target space. Okay. Then now we have some ambiguity because geometry is changed, which means that, for example, if we calculate UV cutoff from the geometry, then which means that the UV is changed. But what we do here is just rescaling the metric. We did nothing else. So it should, I mean, real physical quantities should not change. So we have to deal with this. And I think this is a very important point about the discussion, like I mentioned many years ago, about when they first discussed the UV cutoff of the Higgs inflation. And yeah, and also another important point is that the Higgs inflation actually is a multi-field inflation, kind of multi-field inflation. Of course, when we discuss inflation, only one direction, one linear combination is important. But when we try to discuss this UV cutoff, we have to take into account multi-field effect. So we now need to solve this problem. We have to regain the power of the geometry. Instead of let it be spoiled by gravity. So we have a good method, which is called we extract the conformal mode of the metric. Because we notice that when we do conformal transformation, we are actually changing the determinant of the metric, right? So we can extract, this dot means any frame, Einstein frame, Jordan frame, any frame. In any frame, we can extract the kind of conformal mode out of the metric such that the rest has determinant -1, okay? Then if you do it in Einstein frame, Jordan frame, then the conformal transformation actually becomes just a rescaling of the conformal mode, right? So then if we can somehow include the conformal mode into the target space, which means that the conformal mode will become a coordinate of the extended target space, we call it. Then now we changing the coordinate will not affect the geometry. And this is the essence of this extended target space. And as you can see, by extracting the conformal mode, then the Ritchie scalar actually will contribute a kind of kinetic term for this conformal mode. Okay. Then by adding this conformal mode back to the the kinetic term of the original scalar fields, actually we can have a one-dimensional higher extended target space, okay, including the original phi I and the new conformal mode. And the metric looks like this. Of course, you don't need to care about the detail anyway. I just want to show you this is the extended target space, and I will show you that this is will be very helpful for us to determine the UV cutoff. Okay, and let's discuss some general ON symmetry nonlinear sigma model. Okay, with ON symmetry, generally this metric can be written in the spherical coordinate in this way. Okay, and then you will find that this Gij, Gab, J actually means the Jordan frame because this part is still not the Einstein Hilbert. Okay, Gab will looks like this, and then we can calculate all the relevant Riemann tensor components and something, and you will find that, for example, at this kind of vacuum, which we are interested in, because for example, in Higgs inflation, usually we set all the pi i's 0 and the radial mode, the inflaton we usually talk about, we have some finite width. Of course, this also can be 0, for example, during reheating. And the vacuum for the conformal mode, we chose it to make this the coefficients in front of the graviton will become m Planck, something like that, or lambda g. Okay, lambda g denote the cutoff scale from the gravity sector, which usually is m Planck. Okay, then from this target space, extended target space, we can calculate the Riemann tensor, and you will find that actually the Riemann tensor still has this special structure, this delta, delta minus delta, delta, with a coefficient here. And notice all the indices here is for the IJKL, which is for phi I only. And all the other components, other here means that at least one of these components is related to the conformal mode will be 0. So actually you can immediately know that the conformal mode actually is not contributing to any scattering amplitude because all the Riemann tensor is 0 if at least one of the indices is for phi. So we are kind of including one conformal mode into the extended target space, but it does not contribute to the scattering amplitude. Only the Higgs fields will contribute to the scattering amplitude. But now, since the conformal mode is now part of the target space, it's one of the coordinates. So the geometry of this extended target space will then be independent of the conformal transformation because conformal transformation now is only a coordinate transformation or coordinate rescaling. Okay. Then we can calculate, for example, this general example, we can calculate the cutoff scale for the nonlinear schema model, and you will find that this is given like this. And you have a part that is independent of the gravity, and the other part is due to the gravity, and it will vanish if, sorry, here typo, vanish if we take the so-called conformal coupling, which means that conformal coupling which means that the scalar field actually is minimally affected by the gravity. Okay, so now you will have a method from this extended target space that is independent of the Fourier definition of frame transformation. But still, you can get the scattering amplitude or UV cutoff from the geometry, from the curvature of the extended target space. So this is very nice. Then we can now apply this method to this Higgs inflation. Okay, we know that we should not be kind of misled by this delta ij. Actually, we have to take into account the conformal mode into this, and then you calculate everything. Here, in our paper, we already show you in the table, we already show you all the components that is related. Then immediately you can find out the cutoff scale for the Higgs inflation. Okay, which is looks like this. For example, in the standard model Higgs case, n is 4, so we take this. Then you will find that when the field value, for example, during inflation, when the field value is large enough, the cutoff scale is actually one. Is the cutoff scale, the ratio between cutoff scale to the, for example, m Planck or something, is 1 over square root c. And for intermediate field value, we have this field value dependent cutoff scale. And for example, very small field value, which is relevant for reheating, for example, around the origin, then the cutoff scale is 1 over c. And this is consistent with the known result, for example, given in this paper, which give you the cutoff scale like this. So for, yeah, this is one-to-one correspondence, okay? And have the field valid, field dependent cutoff scale and 1 over n Planck over c, something like this, okay? And for n equal to, since we don't, for n larger than 2, the dominant contribution is given by pi scattering. But for n equal to, we only have 1 pi, so the contribution from the Higgs, H and pi scattering. Okay. Okay, now we know the cutoff scale. Okay. Especially during reheating, the cutoff scale is even lower than the one during inflation. And these people pointed out that during the preheating in this Higgs inflation model, the Ng boson that produced when the Higgs field crosses the origin will be, we have momentum much larger than the cutoff scale. For example, as you can see, every time the Higgs crosses 0, the effective mass of the Ng mode will, will have this kind of spiky feature with very narrow width and very large height. And this means that actually such kind of Ng boson with large momentum can be produced during the preheating. And one can estimate the typical momentum of this Ng mode, which is proportional to the delta t minus 1 over delta t. Delta t is the width of this spike, which can be estimated by multiplying the curvature of the Higgs space and the energy at the end of inflation, which is given by this lambda, a square root lambda n Planck, which is typically larger than this cutoff scale. So it's kind of here. So you have any process involve particles with energy larger than the cutoff scale, which means that we need UV extension. Otherwise, you have suffered from this unitarity problem. Okay. Then let's have a look at I think to me is the most natural UV extension, because as discussed in these papers, actually this R squared term can emerge from this one loop quantum correction in the large N limit. Okay, of course you need to resum all the one loop diagram, like this one loop and the loop and then loop, something like that. Or you need to resum all the one loop diagrams, and then this non-minimum coupling, the loop is from this non-minimum coupling. The loop inside is the Higgs, and it is because we have n flavors, so this is kind of enhanced by n, and also the non-minimum coupling is large, so this is kind of enhanced by large C and large N, and then finally you end up with the counter term like this, alpha R square, and alpha is typically n C square. Of course, you can also have such kind of terms, but they are not enhanced by the large C. So basically, dominant one is this R square term. Okay, so it means that given this Higgs inflation action, and then if we consider the quantum correction, one loop at one loop level, then we have this R square term in the action. So we have this so-called Higgs R square inflation. Okay. So now we can examine the cutoff scale. Okay, in this model, whether it is improved or not. Okay, then we can do, for example, wire transformation to remove this nonlinear Ricci scalar part, and then you end up with a scaleron, just as in the Stravinsky model. Okay, then you have one more scalar field, sigma, in addition to the original Higgs fields. Then now you can use the extended target space to calculate the curvature, and you'll find that actually this extended target space is completely flat, which means that there's no cutoff scale from the scale sector in this model. Okay, the cutoff scale is given by the graviton, which is m Planck. Okay, now we have a much higher cutoff scale than the original Higgs inflation model. Then now, let's look at the reheating process. Okay, yeah, let's skip this maybe. Then the reheating process is no longer violating unitarity, as I can show you, for example, in this one. This is without R squared, the original one. This is with R squared. As you can see, the evolution of the Higgs field is changed in the presence of the scaleron. The upper right corner is the potential of the Higgs. I mean, in this model, this is Higgs axis, this is scaleron axis. Okay, and this sharp transition is changed into many small oscillation due to the presence of scaleron, which means that because as I show you here, this sharp transition actually corresponds to the essential the key spiky feature. Okay, but now since this is kind of uh yeah changed, then we expect that you can expect that by replacing this sharp transition with a finite width, this spike will immediately, you know, get mild, milder, much milder, especially when the Xi parameter is smaller. For larger Xi, it's more close to the original Higgs inflation model. For smaller Xi, this is more like the Stravinsky model. But in any case, the spike now is much milder than the original Higgs inflation case, and which can also be shown in this semi-analytical results. This dashed line is for the effective mass square of the Ng boson, and the blue line is for the width of the spike. Then as here is m, but you can understand that when the right hand side is for larger Xi, more like more like the original Higgs inflation, and the left hand side is more like Stravinsky inflation. So you can see that the width is actually increasing, right? In this case, and also the mass is decreasing when we get closer to the Stravinsky. This is also expected naturally. But in any case, even at the very boundary, actually only when we take really the limit at the Higgs inflation, then we will have such a very violent production or very high energy of the Ng boson. Otherwise, the Ng boson is not as energetic as the original Higgs inflation case, and it will not violate the unitarity. Okay. So how much time, sorry, I have left?
We have 4 minutes.
Okay, then let me very briefly talk about this Einstein-Kahn Higgs inflation. So it's proposed by the Shabashnikov's group, and actually the Einstein-Kahn Higgs inflation can be kind of general framework that include a large class of Higgs inflation models. For example, other than the original one, Higgs inflation is also considered in the Palatini, so Palatini formalism. Okay, and yeah, and so of course, in the Palatini case, we actually don't have such unitarity violation, but the cutoff scale of the Palatini Higgs inflation is still very low. So I also would like to know whether we can kind of improve this low cutoff scale, although it is not unitarity violation, not unitarity violating. Okay, and Then in the Einstein-Cartan formalism, which we include the torsion, so-called torsion, and also include a new term, it's called the Nian term, named after two Chinese physicists. And they introduced the non-minimal coupling between the Higgs field and the Nian term. So by doing this, and here you have a new non-minimal coupling coefficient C eta, and we can define a new parameter R, which is the ratio between this non-minimal coupling and the original non-minimal coupling C. Okay, and then you can find that when R equal 1, you can recover the original Higgs inflation model, while when R equals 0, you will recover the Palatini Higgs inflation. So by going between this 1 and 0, actually you can include a large class of Higgs inflation models. Okay, and of course the cutoff scale of this EC Higgs inflation model is also, you can easily find that they coincide with this limit in the when taking the corresponding R. Okay. So if we study this model for general R, then actually we are studying a lot of Higgs inflation models. Okay, and then we use the same technique by calculating one loop, and then you have a kind of R square. But of course now we not only have R but also the Nian term because the nominal coupling also appears here. So the loop inside when we calculate such kind of loop, this contribution should also be included. Then you will have still you will have only one new scalar field, the scalaron, but the mass actually is controlled by this ratio R, okay, which is given here, for example. Then you can calculate the new cutoff scale, which is given by this, and I can show you the final figure. So this lambda 0 EC is the original cutoff scale for the EC Higgs inflation, okay? And this blue line is the after including the one loop correction. And you find that actually for large enough R, for example, R larger than 10 to minus 4, actually is the UV cutoff is somehow raised up to some value, especially when R is close to 1, actually it's larger than the Planck, so it's okay. But for this close to the Palatini limit, actually the cutoff scale, new cutoff scale actually is lower than the old one, which means that such kind of calculation is not valid anymore. I mean, we cannot do this. So this method can only be regarded as valid for this white background sign. This gray background sign, actually we cannot do that. Okay, and we can understand this as like this. So the improvement of this UV cutoff actually is because of the scalaron, right? And the scalaron mass, as shown here, actually is pretty low compared with this cutoff scale, and so it can coupled and it can play a role in the scattering process. But when we go past to this point, go beyond, and then the mass, because it's inversely proportional to R squared, so you will find that it becomes too large, it decoupled. Actually, even if you have this additional scalaron, it cannot help to improve the UV cutoffs or any other things. So yeah. So anyway, the message here is that we can do this one loop correction, and it can improve the model, but only
We have
for
1 minute
large.
left.
Okay, yeah, this is the last